So we're going to begin our discussion on similar triangles with the definition of similar triangles, and it's pretty straightforward. We say that two triangles are similar if they have the same angles. This means that if we want to check if two triangles are similar, all we need to do is make sure that the angles in the first triangle are the exact same as the angles in the second triangle. So let's explore this definition with our following example. Here we're given triangle A and triangle B, and we need to determine if they are similar. So what we need to do is see if all of the angles in each of these triangles are the same. We're missing one in both, so let's figure out what that is. Let's call this missing angle in triangle A alpha and the missing angle in triangle B beta. Now to determine what alpha is, we know that the measure of the degrees of the angles in any triangle are going to add up to 180, and so we simply can solve for it that way, similar to what we did in the last video. So we're going to get that here alpha is equal to 25 degrees. Now to solve for beta, we know that 105 plus 25 plus beta is going to give us 180. Simplifying over here, we're going to get 130 plus beta equals 180, and then subtracting 130 from both sides, we'll get that beta is equal to 50 degrees. So let's actually go ahead and replace these angles with their actual measures. We know that alpha is 25 degrees and beta is 50. So if we look, we've got three sets of corresponding angles. We've got 50 degrees here, 105 degrees here, 25 degrees here. So these triangles are similar, and we denote that as follows. We say that triangle A is similar to, so that's what this squiggle here means, triangle B, and that's because all of their angles are the same. Now let's look at the next example, example 2. We want to see if these two triangles are similar. So once again, we're given two angles. We know that these two angles both represent 90 degrees, and so we just need to figure out the third angle. So here I'm going to do a little bit of mental math to save on time. We know that 90 plus 60 is 150. So if we subtract that from 180, we'll get this is 30 degrees. This is actually a 30, 60, 90 triangle, and we'll talk a little bit about those later in the semester. In the next triangle, we have that 40 plus 90 is 130, so this missing angle is 50 degrees. So even though these two angles are the same, there aren't any other equivalent pairs of angles in these two triangles. So triangle A is not similar. If we call this A and this B, we have the triangle A is not similar to triangle B because all of their angles are not equivalent. Now Euclid gave us some other useful facts about similar triangles, namely about the corresponding sides of similar triangles. What we know is that if two triangles are similar, their corresponding sides are proportional. And this is going to be very useful to us throughout the semester. So if we look at the above diagram, what this says is that since these two triangles are similar, we get a ratio between their two corresponding sides. So A is going to correspond to A prime, and that's going to be equal to the ratio between B and B prime, which is similarly going to be equal to the ratio between C and C prime as follows. So let's use this fact to determine the length of a side that's maybe missing given two similar triangles. In this example, we know that these two triangles are similar, and we want to find C prime. So we have that here 5 is going to correspond to 7. So we have 5 over 7, and we have that we're trying to find C prime, and that's going to correspond to 15. So 5 over 7 is going to correspond to 15 over C prime. Now to solve for C prime, I'm going to cross multiply. That's going to give me 5 times C prime is equal to 7 times 15. Simplifying, I'm going to get 5C prime is equal to 105. And when I divide both sides by 5, I'll get that C prime is equal to 21. So we were able to use results from Euclid to determine the length of a side of a given triangle just by knowing that it's similar to another triangle, which is pretty neat. So in our final example, we're given 2 more triangles. We know that they're similar, and we want to find the side length of A. So here's A, and we just need to figure out what it corresponds to. So it looks like A is going to correspond to, let's see, if we were to move this triangle a little bit, that's not going to work. Well, let's just eyeball it. A is going to correspond to 3 here. So we're going to start off our ratio by A over 3. And now let's pick this side. So 10 is going to correspond to this 5 here. So we get A over 3 is equal to 10 over 5. Once again, cross multiplying, I'll get 5A equals 30. And dividing both sides by 5, I'll get A equals 6. Now, I also could have figured this out by just seeing that each of these side lengths in this bigger triangle is just kind of scaled up by a factor of 2. For instance, we have 4 here, we have 8 here, we've got 5, and we've got 10. So if I recognize that immediately, I could have just multiplied 3 by 2 to get that A was 6.